Hello everyone, my name is Franziska and I work at the research group of Professor Jucke. In my research I deal with in situ extraction, or to be more exact, with single droplet in situ extraction. But before I'm going to tell you more about the single droplets, I'm going to talk shortly about why in situ extraction is such a great tool. So let's take, for example, the reaction system for the synthesis of 5-HMF. In the aqueous reaction medium, the target component degrades to formic acid and levulinic acid. On top of that, a side reaction to humans takes place, thus lowering the reaction yield. To re-increase the yield, an in situ extraction can be applied, where the target component is extracted into a second organic phase, thus suppressing the yield-lowering reactions. When it comes to the design of tubular reactors, two phenomena need to be considered: the fluid dynamics as well as the mass transfer. As for the fluid dynamics, the rising velocity of the droplet can be calculated by applying a force balance. In the stationary system, three forces need to be considered: the buoyancy force, the gravity force, and the drag force. With rising diameter, the form of the droplet is not always spherical, which reflects in the rising velocity. Droplets with small diameters usually have a rigid phase boundary, especially if there are impurities in the system. With rising diameter, inner circulations of the droplet take place. The maximum velocity occurs for oscillating droplets, where the form varies between spherical and non-spherical. If we increase the diameter further, the droplet becomes deformed and the rising velocity decreases. As for the mass transport, the flow across the phase boundary is induced by a concentration gradient. The mass flow can be expressed by the Fourier number of the droplet. Here, the fluid dynamics are represented by an effective diffusion coefficient, where the instabilities of the phase boundary are summarized by the empirical value CIP. To investigate these phenomena at reaction condition, meaning high temperature and high pressure, a suitable single droplet experiment cell is needed. Here, the droplet is inserted at the bottom and withdrawn at the top for further analysis. The retention time can be adjusted by applying a countercurrent. If you want to learn more about single droplet experiments and what I'm going to do with the results, check out my poster or come see me at the poster session.